Hello everyone, I hope you're having a good day. In today's video, I wanted to cover context window and a transformer architecture and how to make them bigger. This is an especially interesting topic to dig into because we are starting to see models with quite large context windows. For example, Gemini 2.5 has a context window of 1 million tokens and Llama 4 Scout boasts 10 million. I found a ton of great tutorials and resources to dive into each section, so check out the description to explore a bit more in depth. For those that don't know me, I'm Yassine, a published researcher and machine learning practitioner who love to teach. You might be wondering, why would you need more context for these transformers? The issue is pretty simple. Transformers are stateless models, at least in their original form, meaning that they won't remember anything that was imputed into them. So this is a bit problematic application-wise, since there's a lot of benefit from the model remembering past conversation or outputs. There are many techniques to go around this feature of the transformer, but they all depend on injecting the past history back into the context. At some point, this injection just crumbles when the maximum context length is hit. So one very recent example of like having a larger context window in the input is useful is in the DeepSeek R1 paper. As you can see here in this plot, like with R10, at 8,000 step, we're getting better performance, right? So better than like at the 0 step during the reinforcement learning phase. But what's happening here is that as the number of steps increase in the reinforcement learning kind of training, the average length per response is increasing kind of dramatically. So meaning that like if you had a large context window in the input, the model could keep on reasoning for a very long time when it hit like a very hard question or something like that. Although very long context transformers are kind of new, a few tests exist to figure out if the model is making good use of its increase in context size. One of them is the literal retrieval test for LLMs, and it works as follows. Basically, you have a bunch of lines like this, 1, 2, 3, blah, blah, with a random number in there, and at some point, a line will say something a bit like assembly, like go to and then exit, right? So something like this, execute this, go to line 5 and report only registered content without any context or additional text, just a number and then exit, right? And then it should output this number, 6727. And you can make this as big as you want. And then just jam this into LLM and check if it is able to do the task. So a variant of this in the same kind of vein of retrieving something is the Needle-in-a-haystack, where you have a lot of document with a specific topic, right? And then there's somewhere in there where there's an information, the needle, that is kind of not supposed to be there. And then it's placed at different part of the document, either at the top or at the bottom of the whole thing. And this whole thing is shoved into an LLM, and then you're asking it a question that can be answered with this little information that was found inside of the haystack. How to read this plot is that the green is good, red is not good, like in terms of accuracy for retrieval. At the top here, it's the top of document. At the bottom is like at the bottom of document, and then it's like everywhere in between. And this is for a small document. And then you go, as you go to the right, it's gonna be bigger and bigger document. So usually you're gonna have green on the left, and then as you go to the right, you're gonna see some deterioration. A variant of this is what's called a multi-round needle-in-a-haystack, which has more of a natural flavor than like just a bunch of random document and just one thing of interest in there. This is a bit harder to make like a benchmark like this, and the only where I've seen it so far is in the Minimax paper. And the idea here is that it's like a conversation with an actual user in the chatbot. So here you have, please continue writing the follow-up content of this poem, blah, blah. And then the LLM is writing a poem. And then there's a lot of like random stuff that the user and the LLM are saying. And then the user is asking this, write a poem about penguins, another haystack dialogue over there. He asks also again about writing about penguins again. And then mini haystack dialogue again. And in here at the end, it says, please repeat the first poem you wrote about penguins. The golden answer is this: on the peak of Antarctica, blah, blah. It's this one, right? This one that we want. So that's kind of what we're looking for. So it's a bit more nuanced than like the normal needle-in-a-haystack problem set. The last one that is pretty interesting is the MTOB, machine translation from one book, which is kind of becoming more and more useless now. That LLMs are just ingesting like all the random information in the internet. The basic idea in 2024 was that there's this language Calamang, which is not that there's not a lot of people that know it. There's no information on the internet, right? There's like one book that showed the translation between like Calamang to English, I believe. The idea is that since the LLMs are very poor at this task, let's say of translation natively, because they don't know the language, like it could be made up for all they know. When you give the book as input and then you test their translation ability, it shows how they can manage this big book and the task of translation at the same time, right? Just one shot the response. Well, this is pretty cool. The issue with this is that as time goes on, there's more Calamang on the internet or whatever these frontier labs are doing. So it gets better at it, just natively without any training. But it's a very cool idea here too. So at this point, you might be wondering, like, what even is composing the context window, and what is the bottleneck that prevents us from arbitrarily setting it to a huge number? Let's do a quick recap of self-attention so we can pinpoint where the context window actually is and why it was historically small. Here's a classic transformer with an encoder on the left and a decoder on the right. Usually with a BERT type of model, you'll have only the encoder part, and with a GPT type of model, you'll have only the decoder part. If we zoom into one of the encoder or decoder layer, we can see that they are composed of many things. They are notably layer that normalized and feed-forward network. But for the context window, what is of interest to us is what is called an attention layer. There are multiple kinds of attention layer: mask, encoder, decoder. For the sake of exploring the context window, let's take the vanilla self-attention layer of the encoder. Now, if we pop open just the self-attention layer, we can see this diagram. Let's stay focused mainly on the key, v, and q elements. The input vector x comes in and is copied into three paths. Two of the paths in which the input vector is multiplied by a different set of weight to produce q, so the query, and key, the keys. These two are then multiplied together, rescaled, and go through a softmax to generate probabilities like quantities labeled A in the diagram. These quantities are then multiplied by the result of moving the input vector through the weight matrix that produces the value vector v. This whole transformation is carried out throughout each element and can be rewritten in matrix form, like this. The size of Q and K make it so that the intermediate representation of the self-attention matrix is of size n by n, where n is the input length. So during this attention process, we effectively have all of the input tokens attending to all the others through the intermediary matrix formed by Q and K. So to define the context window, it is effectively the maximum size of the input that can go into the input layer and that subsequently populate K, Q, and V while making the model still functional. Now, that specific intermediary attention matrix is very important because it tells us a lot about the powerful representation that self-attention can give to the transformer architecture. It makes the model able to draw a connection from each input to any other input token directly. The weights matrix make it so that different parts of the transformer in a multi-headed attention will attend to different elements to learn a task. This is in contrast to another type of network that was popular a decade ago called recurrent neural network. That network, when unrolled, is a series of elements that are fed in series. The memory of the first token kind of gets diluted as it passes through the network. By the time it hits the last token, it's not necessarily easy to make proper connection between very long dependencies. Now, if you're paying attention, here you might realize that theoretically we could shuffle all the tokens around and it won't change anything in this matrix calculation. We need a way to tag the position of the token as it is important information in natural language processing. This is where positional encoding comes into the mix. In its original form, the other used sine and cosine function of increased frequency in order to encode a token position, which was then added to the embeddings of the self-attention matrix. The idea is to encode position by having a hierarchy of elements that shift at different frequencies, a bit like the binary numbers encoding. Here, the element with the highest frequency have small unit shift, and the element with lower frequency encode larger numbers. We call that absolute positional encodings. It does create some issue with the fact that some token combinations have the same meaning, even though one word is changed placed. So this method was refined some more. It evolved into what is called ROPE, or rotary positional embeddings. It is the same idea of various elements having different frequency of changes, with the earliest having the fastest frequency and later having more slower changes. In this specific case, we aren't looking at an absolute position in the sequence, but the relative position of the inputs. By the way, I'll link to the description a very interesting tutorial on this topic, do check it out. Now that we refreshed our mind about attention and how context windows fits, why can't we just increase the input length at will? There are two major issues that have to do with the way attention is calculated and how position are embedded. If you look at this square matrix, you might be realizing that this self-attention will inevitably lead to a performance problem. Effectively, the matrix is getting quadratically bigger with the input size, which is a problem when you want to jam longer and longer input into the context window. Although we're going to see many different types of attention mechanism in the next part of this tutorial, a somewhat recent paper by Microsoft made the statement that self-attention is necessarily quadratic. This is a result that comes back even with more recent architecture, as the best model always have a mix of newer type of attention mechanism and regular self-attention. It's important to note that this quadratic complexity issue is not present in RNN. A lot of the technique to curb the quadratic problem inevitably transform the transformer towards an RNN-like architecture. The quadratic complexity of the self-attention calculation is not the only issue that exists with large context length. Positional encoding also put an upper bound on the size of the context you can use in the model. The main issue is that there's a degradation of the performance past the training context length, where we see a rapid performance drop. Now that we know the problem, let's look at the solution that made these new models with larger context windows possible. So there are two main buckets of fixes to increase context length. The first one is positional encoding based and the other one is attention calculation based. You need to use both to unlock the largest context length possible. For fixing the positional encoding issue, we have a few techniques that were developed over time. The core idea of each of them has to do with position interpolation with the new input size, meaning that we downscale the new larger input position to match what the model was trained with. This is in contrast to extrapolation, which will increase the position embedding into a range that were never seen before to accommodate larger input. As we can see, everything theoretically stays within the pre-trained range, it's just that now it has a finer resolution. The vanilla version of position interpolation for row-based system is good, but there are some performance downsides. In a recent controlled study on long context extension, the author compared a whole lot of different methods and different architecture for context extension. What they found was that the neural tangent kernel interpolation of rope was the most robust version and could generalize well to longer unseen sequences. The idea is to not interpolate each of the rope frequencies the same way. As shown in multiple studies, the positional information in the high frequency component is very important for the transformer architecture. Therefore, the NTK positional interpolation leave largely the high frequency alone and modulate more aggressively the lower frequency. This makes the NTK rope model very performant, as we can see in the Needle-in-a-haystack task in the bottom row with NTK 32K. The dotted line is the longest sequence seen during training, and it can still get pretty good performance on the 64K input. That's the basic idea for position interpolation, but do note that other methods exist like CLEX here. I highly recommend the paper, and I have two interesting YouTube tutorials that break it down in the description. The second type of fix is related to the quadratic complexity of the attention matrix calculation. There's a ton of way to fix the quadratic issue, but I'm saying here fix and not fix because it has been shown time and time again there is something special about having all inputs attending to all the other ones. So most of these solutions, even if they extend context, have a hard time competing with the full softmax attention. So it comes as no surprise that the core focus of improving transformer was instead put into making training them much more optimized to run on GPU. One such widely used optimization breakthrough is flash attention by Dr. Tridao. The others of flash attention figured that the part that was taking the most time during attention calculation wasn't even in the attention calculation. It was in reading and writing to the slower part of memory. Therefore, they made a GPU-aware attention mechanism that makes more optimal use of the faster part of the GPU. The second version of flash attention is now widely used in most implementation of attention in transformers. This highly performant implementation of attention led to some problem in developing alternative attention mechanism, since The algorithm and the hardware are so tightly optimized, a similar amount of effort need to be put into alternative attention mechanism to even come close to flash attention. Some of that hardware synergy has been done with linear architecture like lightning attention or Mamba. But before diving into these, let's look at some early attempt at optimizing the attention calculation within the attention matrix using sparse attention. The idea is very simple. Instead of calculating the full matrix of attention between each input tokens, we trim it down in various ways. The closer we stay to the diagonal, the more attention each token gives to its surrounding. This is what is happening in the sliding window attention mechanism. You can also skip some tokens so that the token aren't attending to those right next to them. This is called dilated sliding window attention. This technique was used, for example, in the WaveNet architecture almost a decade ago for audio generation. Or you could also have a few important connections between some token position that have access to the full global context. This is called global window attention. Mixing these strategy is what sparse attention is all about. In one of Ilya paper from 2019, the authors realized that they could reduce the complexity of attention matrix to n by n square by using a specific sparse attention structure with some global element and some sliding window without too much performance loss. In 2021, the idea was refined some more with the big bird type of attention matrix, which has a very weird shape when you first look at it. The core idea is to do a mix between global attention, window attention, and just enough random attention. This makes the big bird attention linear with respect to the input. The other made use of graph theory to create a adjacency matrix that keeps some of the key property of transformer attention while reducing the number of connections. A bit like what is going on in the connection between different brain regions in human, which has what we call a small world network architecture. A more recent paper from literally last week did a full analysis of the different type of sparse attention currently in use and compared them on the newest language models. The paper is going into a lot of depth to quantify the usefulness of sparse attention in the two phases of LLM inference, namely the pre-filling phase and the decoding phase. Both have different dynamic depending on multiple factors like longer or shorter sequences, as well as the type of sparsity. The first result figure is very information dense, so let me walk you through it slowly. We have two plots, one for shorter sequence of 32K and one for larger sequence of 128K. The different shape are the different size of Quen. The coloring is a compression ratio, so that means the hotter color means the sparser the model. The y-axis is the performance, and the x-axis is the computational budget. So for the pre-fill phase, we have the following results. For shorter sequences, increasing density or size provide gains. The denser the model, the better the performance at a similar size. Some denser, smaller models are performing better than sparser, bigger model on smaller compute budget. For longer sequences, the sparsity perform best at a given computational level, meaning that a sparser, bigger model will perform better than a denser, smaller model for the same amount of compute. For the decoding phase, we have the following results. So for shorter sequences, we have similar pattern where increasing density or size provide gains, but here the denser model are performing better at all sparsity level. For longer sequences, we have the same story as before, where a sparser, bigger model will perform better than a denser, smaller model at a similar compute level. The paper also showed that there is no one sparse attention method that works better across all task types. There's always a degradation on at least one task, highlighting that sparse attention is not like a universal solution. So do check out the paper, it's a very complete review on this particular subject. Now we're going to get into the more extreme changes to attention matrix calculation that make use of low-ranked decomposition methods. Sparse attention is a change, yes, but it still makes use of the same n by n attention structure. The low-ranked decomposition method makes use of a projection to calculate roughly the same thing as the n by n attention matrix, but in linear time. The idea is that instead of working with the big n by m matrix on the left, you can decompose it into two matrices of common size k that roughly approximate the bigger matrix. This strategy was leveraged in 2020 by studying the rank of the self-attention matrix in transformers. What they showed was that the attention matrix has usually a low rank in practice, with the 128 eigenvalue decomposition returning most of the information. Therefore, the idea of linformer is to use a projection to these components for the value and key parameters. The gist of it is that there are no n by n matrices that are being used now, and quite a few k by n matrices, with k being the smaller projection dimension, making this whole thing effectively linear time. The performer architecture follows a similar line of thinking, but instead use kernels to figure a way out of softmax. Remember that softmax is kind of what is preventing us from doing the k-transpose.product v shortcut. The idea is to use a kernel technique that they call fast attention via positive orthogonal random features to approximate various kernelizable attention mechanism beyond softmax. With this new kernel trick, we can multiply this new k and the original v first. This way we never materialize the n square matrix. Another way to attack the problem is to keep the original attention calculation, but to start to modify the inner working of the transformer to kind of chunk the calculation so that the costly calculation are restrained to a smaller part of the network. This method is called chunking. One of these ideas is the gated attention unit that appear in the paper Transformer Quality in Linear Time. The gated attention unit combines the idea of a gated linear unit and multi-headed attention into the same component. Basically, it is a modified gated linear unit with a gating mechanism that allows for the use of a weaker attention mechanism without significant loss in quality. The others show that doing it this way, you can pop out softmax and replace it with something much simpler to work with, like a ReLU. This simplifies the computation of the K and Q matrix. In a nutshell, the K transpose.V matrix, which we can denote M, can be iteratively summed like in an RNN. But that attention calculation within a chunk can use the more expensive quadratic calculation. So in this case, the other seems to have the best of both worlds. They split the input into chunks and use quadratic local attention inside each chunk, just like regular GLU, and linear global attention between the chunk. They report results very similar to the basic self-attention transformer with much less complexity. Another more recent method making use of chunking is called lightning attention. The idea is quite similar to gated attention unit and chunking of the attention calculation, but on top of that, it makes use of flash attention type of GPU optimization to make the performance competitive. This lightning attention idea was recently added to the Minimax Text 1 architecture with great result on long context tasks. Interestingly, the full architecture makes use of a mixture of lightning attention blocks and softmax attention block in a 1:8 measure for top performance. Seems like the chunking methodologies are highlighting that there is something valuable embedded inside the traditional softmax calculation. So the last type of the last type of fixes that we can see here is really to rethink the full architecture from the ground up and try to come up with something completely different that doesn't have the same drawbacks as the original transformer architecture. Megabyte is one such approach which takes the chunking to an extreme by breaking down the quadratic matrix multiplication into a composition of multiplication of smaller matrices. The idea was to develop an efficient architecture for modeling long byte sequences without relying on tokenization, which can be lossy and complicate processing and multimodal modeling. So the Megabyte stack two transformers together, one for patch embedding and another one for individual tokens inside the patches. The resulting architecture can achieve sub-quadratic complexity with these changes. Another interesting method taking a very different angle is infinite attention, coming from a 2024 paper. The idea is to add some linear attention into the mix where the model will compress the information into memory while still having the causal dot product attention. This is very interesting because if you stop for a while and think about the changes, the shadow of the RNN is not too far behind. Another attention compression method that was published at the end of last year is Titans, which kind of pushed this memory compression idea forward even more. So the idea is to have this type of parallel compressed memory that could be jammed back into context whenever needed, but inside the model. A bit like in RAG, but internally to the model mechanism. There are many strategies to set up that neural memory. Memory as context, memory as gate, memory as a layer. The conclusion of the others is that these Titan architecture excel at long-term memory tasks, but there is compute trade-off between efficiency and expressiveness. They highlight that it is quite important to manage memory effectively with forgetting mechanism to prevent overflow in very long context tasks. Another line of reasoning led to the S4 architecture, which are kind of bridging what makes other techniques like CNN and RNN great. For instance, state space model can naturally handle irregularly sampled data. It can be expressed as a convolution if needed, enabling efficient computation, or can be computed iteratively, similar to RNN. So this model made use of a whole lot of techniques we've discussed earlier, like low-rank approximation, but combined them in a way that really doesn't look like a transformer anymore, and used also ideas that were not even in the realm of transformers. This eventually led to the well-known Mamba architecture in 2023, which pushed the idea of state space model further with techniques coming from the same vein as flash attention. Finally, more recently, we have Lemma 4, which although we don't have a ton of information on, is able to achieve surprisingly long context with a scout version of 10 million. Interestingly, they make use of hybridization in the layers, with some layers that are devoid of positional embeddings. These are called nope layer, and this modification was implemented on the Common A paper by Coer a few months back. They also make use of inference time temperature scaling for length generalization, aka scalable softmax, that replace softmax in case of variable input length. The core idea for this last bit is that the maximum element of the vector output by the softmax function approach 0 as the input vector size increases, causing the attention distribution to flatten as the context size grows. So having a scalable softmax helped dampen this effect a bit. These changes had an impact on the core models, Maverick and Scout, ability to manage very long contexts. As you can see here on the middle and right side, Scout can find a needle in a haystack up to 10 million tokens, or 20 hours of video content. This is cool, but one of the main criticisms from users was that these models were only trained on 256k context window, so the 10 million context is theoretically nice, but practically not as exciting. Hopefully more information will be shared in the official, not half-baked release about how these models really work, but it shows that we should expect an increase in context length of frontier model in the near future. To conclude, let's hear it from Nikolay Savinov from Google, who is leading the long context training at Gemini.
I'm curious about the sort of long-term direction from a fine-tuning, or maybe not from a fine-tuning, from a long context perspective. Like, what can folks look forward to in the next 3 years for long context?
So I'll make a few predictions. What I think is going to happen first is the quality of the current 1 or 2 million context is going to increase dramatically, and we're going to max out pretty much all the retrieval-like tasks quite soon. After that, what's going to happen is the cost of long context is going to decrease. And I think it will take maybe a little bit more time, but it's going to happen. And as the cost decreases, the longer context also gets unlocked. So I think reasonably soon we will see the 10 million context window, which is like a commodity, and going to say 100 million, well, it's more debatable. I think it's going to happen. I don't know how soon it's going to come. And I also think we will probably need more deep learning innovations to achieve this.
I hope this was useful. Don't forget to like if it was the case, and see you on the next one.